unsure where this is going to lead. Actually, what I'm unsure about is how much time and, if any, examples related to Bayesian inference. But I'm going to get started with this guy. So, we have celebrity on board. Thomas Bayes was born in 1701. He's English. Died in 1761 at the age of 59. This is one of the most fascinating tales in the history of science. Somebody very likely you've never heard of, who's been extraordinarily influential and whose work is becoming, here in 2013 and had maybe for the last 20 years, more and more influential every year in every phase of science imaginable, not just the social sciences, but any hard science you can name, certainly in medical research, any kind of research involving numbers. This guy is a rock star. Thomas Bayes was a Presbyterian minister, and his father before him, a Presbyterian minister, and he was also on the side a scientist and a probabilist, and studied and was interested in probability. He became known to the intellectuals of the day and was elected as a member of the Royal Society, the scientific group in England, in his lifetime for having written an essay that defended Newton's calculus. That's Isaac Newton. And he never published anything else except one thing, sort of a theological in nature. He did a lot of work, though, behind the scenes, and when he died in 1761, a friend of his, Richard Price, I don't know anything about this guy. I'm going to put him on the board. I can't remember anything about this guy. I should say there's a wonderful, wonderful book. Very sort of a popular science book out in the past 5 years on Bayes and Bayes' theorem, the history of Bayes' theorem, which is listed right below. And when we're in class, or maybe in a subsequent video, I'll identify it. Richard Price is a friend of his who, when he died, he had his papers. And in his papers was something called an essay towards solving a problem in the doctrine of chances. An essay towards solving a problem in the doctrine of chances. It was an essay about probability, and it included a statement of this. This is Bayes' theorem. Sometimes called the theorem of inverse probability. And you can think of these as elementary events. We're going to replace this with hypothesis and evidence. Probability of A given B, is a conditional probability, is equal to the probability of B given A times the probability of A, all divided by the probability of B. That's a really straightforward, easy thing. You can memorize it, I insist, actually. Memorize it quite easily. There's kind of some weird terms in here that become eliminated when I move from speaking of simple events and start talking about hypotheses. And on the one hand, and data on the other. I'm going to translate this right away. So we're going to make, for the simple event A, we're going to replace that with hypothesis. So you've got an idea about how something works, right? Given, and then you also have evidence. I'm just replacing the simple events B and A with H and E. And let me move this down. Right away, you see something a little different than the frequentist model. It's talking about the probability of the hypothesis. Now, the p-value that we spoke of is not the probability of the null hypothesis. And some textbooks write that, and it's just not. It's just not. The p-value is exactly what I told you it was. Now we're speaking about probability of a hypothesis, its truth or falsity. You can make h equal 1 if hypothesis is true, h equals 0 otherwise, given some evidence. This is a subjective view. subjective view on the idea of what probability actually is. So, the past few videos we've had us featured frequentist objectivist view, where in the coin toss example, probability itself sort of adheres to the coin and not the researcher. There may be a hidden variable somewhere, but all you're doing is flipping the coin. Or in the BEM example, all you're doing is alternating randomly whether the person sees a romantic picture or an erotic one. And probability adheres then to the choice. Bayesians are different. They talk directly about probability in the subjective sense, about what the researcher believes. Let's fill this out first. Probability of a hypothesis given the evidence is equal to the probability of the evidence given the hypothesis times the probability of the hypothesis divided by the probability of the evidence. Now, there's something weird emerging here already, the probability of the evidence given the hypothesis. Sort of it's what's called inverse probability. Where this time seems to be flowing both ways here. Given means already happened. So the probability of a hypothesis given the evidence means you've already made the hypothesis, you've already got the evidence, and now you have the hypothesis. This goes back the other way, as if evidence could appear. And there's a strong criticism of this in the literature from frequentists. I'm not very bothered by it. Probability of the evidence given the hypothesis can, in fact, lead me to a discussion that we'll get right at the very end of the term and not on video about ethics and research. We need to take this for what it is. It's a subjective view of probability. It means that you sort of come to the table with an idea of what is true and what's not true, and an estimate sometimes of the probability of whether your hypothesis is true or untrue before you ever observe the evidence. There are two terms in here worth identifying. One is the probability of the hypothesis. And the other one is here. Probability of the hypothesis is, in the Bayesian framework, your sense of the validity of the hypothesis before you ever do the evidence. And the posterior probability is given here. It's the after effect. So P of H is the prior probability that you, the researcher, associate with whether the hypothesis is true or not. And this is what you find after you view the evidence. This is a very powerful, extremely powerful setup. It allows a combination, just as we talked about early, a combination of induction and deduction at the same time. So remember induction. Inductive research, let's call it, and deductive research have tended, in my life cycle in the profession, have tended to divide quantitative from qualitative researchers. The inductive idea is that you immerse yourself first in the data, like look around, immerse yourself in the data, and then from the data you develop, from watching, from observing, you develop theory, and maybe develop hypotheses. The deductive alternative is that you start with your theory, you develop from it hypotheses that the truth or falsity of these hypotheses would reflect on the purchase of the theory, and then you go to the data. Bayes kind of have all of this. Bayesians kind of have all this at the same time. And to acknowledge that you arrive at a problem, a research problem, having already thought about it, having already contemplated whether you think your hypothesis is true or false. And not only that, but maybe you can even quantify your prior belief and the truth or falsity of a hypothesis in advance of collecting data. In advance of collecting data and testing it on the posterior side, the probability of the hypothesis giving evidence. So Bayesians are acknowledging that we've all been here if we're going to do research. So it takes that sort of, I don't know, maybe false sense of objectivity. I like the objective part of the frequentist thing. Well, more on that later. And yet, it is kind of contrived. Who, for instance, would ever test a hypothesis never having wondered, never having thought, almost nearly with certainty, that you knew what the outcome would be? It's because we've been in the data qualitatively. I've been watching politics all my life. If I make a hypothesis about how something works in politics, it's because I've been in the data and viewed the data and developed theory and hypotheses, and then gone down here and begun to test. Bayes' theorem allows us, if you embrace this as a theory of inference, it allows you to acknowledge that. But let's think about Professor Ben from Cornell for just a moment. I'll give myself some room. And let's think about his result. So he's got 0.031 is the difference between what you would have gotten by chance across these erotic versus romantic manipulations, and which was be 0.5, and what he really got, which was 0.531. That stands up to the frequentist model of statistical inference and allows him to conclude that he has a statistically significant result showing that Cornell students, at least 100 of them, experience some kind of foresight into the future relative to a stimulating or potentially stimulating object. And Bayesians hit the wall when that was published in the Journal of Personality and Social Psychology. They hit the wall and said, here finally is very prominent and frankly embarrassing evidence that the frequentists had it wrong all along. A simple Bayesian prior on the hypothesis. The prior in the context of the frequentist is there is no prior. So we're going to stand this up as a null model and say that it's equally likely that people have ESP or they don't. That's what it means to set in Bem's experiment a null hypothesis of 0.5. It means that ESP is equally likely. The set of people in the experiment, it was equally likely that they had ESP versus that they didn't. Bayesian says that's preposterous. You've already bathed in the data. You've already been around. You know a little bit of physics. You know seeing into the future in that particular way, you know it's impossible. And as a result, you would want to attach here, in building the posterior, your conclusion, which is the probability of the hypothesis given the evidence. You're going to let that be affected in the Bayesian perspective quite heavily by what you believed about the probability of the hypothesis in the first place. So a complete disaster for the frequentist perspective is to say physics illustrates clearly that what you just saw is not actually ESP, but rather a quirk of the frequentist model, which admits that 5 times in 100 you're going to get a quirky result. Now, Professor Bem has been criticized by frequentists too because he published 9 results, or had 9 experiments in his paper, and they all tended to point in the direction of some kind of unusual, let's put it frankly, impossible actual result. And the Bayesians are recognizing and taking advantage of the fact that the frequentist perspective admits from the outset that 5 results in 100 are going to be really weird. And if you do enough experiments, it's a big controversy with Professor Bem. The question is not what he reported, it's what he didn't report. If you do enough experiments, you're going to find funky results. And the Bayesian says, I'm going to throw in the towel here on the pretense that we don't know anything subjectively about the truth or falsity of a hypothesis before we actually go and study a problem. And in many cases, I'm actually going to go ahead and attach a prior probability. In the case of the Bem study, the Bayesians immediately were able to predict, to produce what was going to differ by by Bayesian, by person, to establish sort of ranges of prior belief in ESP, setting it pretty low. We'll find this 0.031 result to be not very reliable. Bayesians eschew, and I'm here pondering how deeply I'm going to go into this, they eschew the idea of the confidence interval in terms, and shun that off to the side, speak instead of what they call credible or credibility intervals. And a credibility or credible interval for a hypothesis or outcome or evidence, this the posterior, probability of the hypothesis given the evidence, would be a much more stringent requirement. Not a null model, where the probability that a person has ESP is 0.5. Not a null model like that, even though it is a flip of a coin in the demonstration or in the experiment itself. It is said the probability that a person has ESP at 0.01, which frankly I think is extraordinarily generous. The probability that anyone has ESP is very, very generous, in my opinion, toward the hypothesis in the first place. In that case, if you do the math, and I'm sitting here pondering whether we should, I think I'll just do a simple problem, and maybe when we do chi-square, show you an R version of, talk to you about an R package that allows you to compute Bayes factors for contingency tables. But for right now, this 0.031 from the perspective of a Bayesian who built in his or her prior beliefs about the truth or falsity of the hypothesis, that 0.031 would be completely not significant, even though significance is really not part of the Bayesian lexicon. So some criticism of Bayes to end this brief, and this may be the end of Bayes for the course. Some brief criticisms at the end. I like the objective idea of probability attaching to the coin. I like it because I study politics, and all the people I know who study politics have perspectives. They have ideologies, and we're all frail humans and have biases in how we think. I like the idea that we can use the objectivist understanding, the frequentist understanding of probability to distance ourselves from a problem. Let's give Bem all the criticism he deserves, and let's also say that he did just set up the problem and let the data fall where they fall. And insofar as anyone knows, no one I know has accused him of manipulating the data. And so I like that sort of distance. So it allows us then to not assume so much, and this is an outrageous thing to assume that maybe there is ESP. But if we assume everything out of existence and rely just on the subjective self, we've got problems where we can introduce bias from the researcher's subjective view. Probably second, just going to differ from researcher to researcher, from problem to problem. So we can let Professor Bem I don't know if he does, might actually believe in ESP. If he does, his priors, as he set this thing up as a Bayesian problem, his priors are going to be very, very different from mine. My prior is not even prior probability, is not even going to be 0.1. It's going to be 0.0000001. I don't believe in ESP because I believe in physics. And so this is a problem for science, to move forward in a strict Bayesian format, because we will, as individual Bayesians, bring different degrees of prior belief. So those are criticisms of it. At the same time, the strength should be obvious, that you recognize and admit up front that you have an idea about how this thing is going to come out, and then you revise that idea rather than create it from whole cloth or from a sort of contrived null model. You revise that idea once you've observed the data. Bayesian statistics didn't catch on, by that name at least, didn't catch on until the 1980s in economics, until the 1990s in political science, and sort of in this decade there's been an explosion of work that is grounded fundamentally in the Bayesian perspective of how you ought to go about doing statistical inference. And the sort of, I would say, concentration of Bayesian political scientists are in very, very prestigious appointments and institutions. If that says anything about who's right, I'll let you decide. That's an introduction to Bayes. I think I will come back, not promising, but I think I will come back and do a video of a Bayesian problem contrasted. It's got to be very simple because some of this can get out of control hard. But a little simple Bayesian problem, and show you how it might differ from the result of the frequentists. This one's over.